Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 19, 2025, which was about 5 days ago. The big takeaway is a method that persistently removes harmful knowledge from large language models while keeping useful abilities intact, delivering state-of-the-art overall performance and better forgetting versus retention trade-offs than prior approaches. The paper is titled CRISP, Persistent Concept Unlearning via Sparse Autoencoders. And as we will see later, the implications for model safety and maintenance are quite significant. Beyond the headline, the method targets specific features, uses parameter-efficient fine-tuning, and consistently preserves fluency and general knowledge. Building on that, two tweets highlight persistent, interpretable unlearning using sparse autoencoders, claiming better safety trade-offs without losing utility on bio and cyber tasks, with moderate engagement around 70 likes. Alright, we are looking at the overview figure, which sketches the two-step loop that powers the method. You can see the left icons marking target and benign corpora feeding into the language model diagram, which indicates where sparse autoencoder features are recorded. Then the right hexagon illustrates the feature bars that get suppressed on the target set, while the curved arrows show the iterative process. The key idea is selective dampening of features activated by harmful data, so benign activations remain intact. Now we are looking at the main results table, which compares methods across bio and cyber domains for two base models. You can see an overall score column that combines all metrics, followed by unlearned accuracy, where lower is better, retained accuracy, MMLU, fluency, and concept. The standout pattern is that CRISP consistently posts the highest overall score while keeping retained accuracy and MMLU strong, which signals balanced forgetting and preservation. Notably, ELM sometimes lowers unlearned accuracy slightly more, but it does so with bigger hits to retention and fluency. Next, we are looking at a side-by-side qualitative figure that contrasts model generations after different unlearning methods, which helps illustrate fluency and topical control. The full panel shows two columns for Gemma 22B and Llama 318, with rows for the original model, RMU, ELM, and the new approach. You can see repetition and artifacts in RMU and ELM, including broken markup and looping phrases, so coherence drops. In contrast, the blue-shaded rows show clear, on-topic explanations that keep benign biomedical context while avoiding harmful specifics. Moving to the trade-off plots, we are looking at retain accuracy on the vertical axis versus unlearn accuracy on the horizontal axis for biotasks, with the red star marking the ideal balance. You can see dense blue clusters that sit close to the star and trace a strong Pareto envelope, which shows many configurations achieving low unlearn accuracy while keeping retention high. In contrast, orange squares drift downward or scatter, indicating worse retention for similar forgetting. The green triangles track in between, but they rarely match the blue frontier. Continuing the trade-off view, we are looking at two scatter panels that map retain accuracy on the vertical axis against unlearn accuracy on the horizontal axis for the cyber domain. You can see dense blue clusters sitting near the red star in both panels, which signals many settings that forget effectively while keeping retention stable. The green triangles trace a competitive frontier, while the orange squares fall below it, so they give up more retention for similar forgetting. The solid envelope lines outline the best configurations across unlearned buckets, reinforcing that frontier shape. Bringing it together, the method delivers persistent forgetting with better retention because it targets interpretable sparse autoencoder features and suppresses only the harmful ones. Two takeaways stand out. The trade-off frontier clearly favors this approach, and generations stay coherent on benign topics. A sparse autoencoder is a tool that maps activations into human-readable features. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.